Hey everyone, today we're going to be looking at graphing motion. We talked briefly about it yesterday in class, and you may have seen it in IPC before. But today we're going to be doing a lab. Virtual students, you're going to be doing a slightly different activity because you don't have the lab equipment. That will be posted as an alternate assignment for you in Google Classroom, so you can go check that out. But you can watch this video to figure out what graphing motion is all about. So you're in physics. Physics is about describing motion at its very basic level. There's some other things involved, but at its core, it's about describing motion. And one of the best ways to describe motion is with math, which is what most of this course is going to be. It's using math to describe motion. But it's really, really hard to picture math, which is why we learn this method called graphing. In math class, the best way to see what's actually going on with an equation is using a graph. So we're going to learn how to graph motion so we can visualize it a little bit better before we get into the super math heavy portion of the course. In order to do that, we need to talk about a few different terms and their variables. We did go over these in class yesterday. Virtual students, you may have done your assignment yesterday and found these definitions, but we're going to run through them really quickly again, just a few from yesterday. The first thing is position. Position is simply where an object is located, where it is physically in space at some point in time. And we're going to represent it as the variable x. Sometimes later on we might also use y, but for now we're just going to stick with x, and it's measured in meters for this class. These little brackets always indicate a unit of measurement. So we're going to do position as the variable x measured in meters. Then we have displacement, which is defined as the change in position. In order for there to be displacement, something has to move from one place to another place. And that is called a change in position. If position is where it's located, displacement is a change in location. And we represent that using this delta, which is a Greek letter. That means change in physics anyway. In Greek, it's just straight up a letter. But the little triangle called a delta, it means change. So if we're doing change in position, we use delta for change, and position is x. So we do change in x for displacement. And it's also measured in meters. Next up, we have change in time. Similarly, we are going to use a nice delta for the change, and time is the variable t. And lastly, we're also going to be looking at velocity, which is how fast something is moving in a particular direction. It is the variable v, and it's measured in meters per second, because it's how many meters you would go in 1 second. And the equation for velocity, which we looked at yesterday and you may have seen before, is velocity equals delta x over delta t. You're not actually going to be calculating anything with that particular equation at this time, but we're going to see how it relates to these graphs here in a minute. The first type of graph we're going to be looking at is called a position time graph. Now, position time graphs are pretty cool, but they're a little bit mind-bending on the mathematical portion if you've never seen one before. So in math, you learn that this horizontal axis is x and the vertical axis is y. But the thing about physics is that we measure and use a lot of things that aren't x or y. Very rarely do we do a graph that has both x and y. So you need to erase these things from your mind and realize that these axes, the horizontal and the vertical, can be any variable that we choose, anything at all. And what we're going to choose is to put time on the horizontal axis. Time, and it's going to be measured in seconds. And then for position time graphs, we do position, which is the variable x, on the vertical part, and we measure it in meters. So position time graph has position, which is the variable x, on the vertical, and time on the horizontal. And we would use these to graph some motion. And the way you graph motion is simply by recording how an object moves. So we're looking at 1D motion right now, which is in one dimension. So we're going to imagine an object that moves on a number line. In class, I'll actually like walk around and move, but you can't see me doing that. So I'm going to do it on a number line. And you have to choose a point that's going to be 0. This place is called the origin. So this is going to be my directions of motion. I can move anywhere along this line. And 0 is the origin. I just chose a place to be 0. Usually we put it in the middle. It really doesn't matter. Now, the other thing that we have to consider with position time graphs is direction. So we've got 2 directions we could go here if we start, well, really if we start anywhere. We can go either to the left or we can go to the right. So any graph that we draw has to include the information if we're going left or if we're going right. There have to be 2 directions in the graph. And the way that we do that is by representing them as positive or negative. So we can choose which way is going to be positive and the opposite way has to be negative. In my graph, because I like conventions and I like things to be as normal as possible, I'm doing positive to the right, as you usually see in math, and negative to the left. So anything that is over here on the left side of the origin is going to be a negative number. Not because it's less displacement, but it's just displacement in the negative direction. And then on the right, they'll all be positive numbers. Now I am going to move my, let's see, I have a red dot. I'm going to use this red dot here, okay? This is what I'm going to use. I'm going to put it on my 0 to start with, and I'm going to move it to the right, okay? So say I go from 0 to 2, but I go kind of slow, so that after 1 second, which is not really true, I'm at a meter, and after 2 seconds, I'm at 2 meters. So all my dot did was it started here, moved that direction. To graph that, you have to choose the object's starting point. So at the very beginning, when time is 0, that is way over here. When time equals 0, my x was equal to 0. I started at the center. I started right there. However, you could, or I could have started at any other point if I had wanted to. If I'd started at 4, my first dot would be up here at 4. If I started at -3, it would be down here at -3. I just chose to start at 0. So my dot starts at 0 when time is 0. And then after that, after 1 second, I ended up at 1 meter. After 2 seconds, I ended up at 2 meters. So I went this far. I've got a straight line there. That will describe my motion. That line says I started at position 0 and I moved from 0 to 2 over the course of 2 seconds. It's pretty simple. So we're going to continue that graph. I know it looks crappy, but I started at 0 and I moved slowly to 2. And now I'm really tired of moving my pin, so I'm going to rest on 2 for a few seconds. Let's see what that would look like on the graph. I'm going to rest on 2. So at 3 seconds, and 4 seconds, and 5 seconds, however long I rested, I'm not moving because I'm just sitting there on 2. So all of those points through all of those seconds are just on 2 the whole time, right on 2. So that flat line there is not moving at all. Now let's say I stay on 2 for all of my time up until 5 seconds, and then I decide really quickly to move down to -3. Say it only takes me 2 seconds to move down to -3. After another 2 seconds, which is going to be 7, I get all the way down to -3. I know these things aren't to scale. I'm so sorry. So I'd, at second 7, be at -3. So I'd go from 2 to -3 over the course of those 2 seconds. That was my third little leg there. So all I did was I started at 0, moved up to 2, hung out there for a little while, and then moved all the way down to -3. That's all that happened. But something else is significant in these graphs. You can see the 3 sections look different because of their slope. And slope is a mathematical thing for lines that you should know how to, or should vaguely know how to calculate by now. And we're going to look at it. You should know from math class that slope equals rise over run. You've probably heard it a million times. We're going to look at what that actually means on this particular graph. If I need to change pen colors. If I want to find the slope of, let's say, this section of my graph, if I was going to find the slope of that, I would do rise over run. I'd look at how much the rise was, which is this much. And if you're looking at just the rise, that is changing position. It's still all on time equals 0, so the only thing that's changing in that little section is position. And we write change in position, which is the rise there, as delta x, change in position. Delta is change, x is position. You would write run as going this way, your position stays the same, but you're changing time, you're going from 0 to 2. So it's a delta t. Your slope is delta x over delta t, which looks suspiciously similar to something else up here. It's the velocity equation. So what we're getting at here is that slope equals velocity for the position time graph. Now, if there's a greater slope, or it's steeper, that means it has a higher velocity. So we had this part here. There's kind of average steepness. I was going pretty slow. This part here that has no slope, no velocity, I was just sitting there doing nothing. And then this last section that's steeper is going faster. So the steepness of your slope will tell you if you're going faster or slower. Flat equals slow and steep equals fast. The other bit of information comes from positive and negative slope. So if I've got a positive slope, like this one here, we know positive is up and to the right, that meant I was moving this way. I moved from 0 to 2. I was moving towards the positive. And then down here, or over here, my slope is negative because it's going down. In that case, I was moving from 2 to -3. I was going in this negative direction. So with the slope of these graphs, the steepness will tell you, like the speed, how fast you're going, and whether it's positive or negative will tell you what direction you are going in. And I promise this one won't take as long. The other type of graph that we are doing is the velocity time graph, which is similar in that time is going to be on our horizontal axis measured in seconds. But this time we're going to look at velocity. Velocity is going to be measured in meters per second. So it's going to be time and velocity. And velocity is how fast you're going in a certain direction. So we're going to take that same scenario that I was doing earlier with my other graph. I'm going to have a number line, 0, 1, 2, 3, 4, -1, -2, sorry, I'm bad at drawing, -3, -4. Also, I'm doing this late at night, so there you go. Starting at 0, moving slowishly to 2, hanging out there for a few seconds, and then we move kind of fast to -3. So if I was going to graph that, I would start off on my 0, and I would be moving from 0 to 2. And I'd be moving kind of slow, but still moving. So I need to figure out what my initial velocity is. So for those 2 seconds, when I was moving from 0 to 2, my velocity was about 1 meters per second. Because if you go look at the slope on that other graph, it was about 1 meters per second, or exactly 1 meters per second. So what I need to do is say I started off going 1 meter per second. And I went 1 meters per second the whole time that I was going from 0 to 2, which is like 2 seconds. So from 1 to 2 seconds, I was going this speed, going 1 meters per second. And then I stopped. I stopped and hung out there on position 2 for a little while. I did that until like second 5, I think. So during that whole time, my graph was flat. If my graph is flat and I have 0 slope, I have 0 velocity, which means I'm chilling down here on the 0 velocity for that whole time. And then after that, I decided to go from 2 to -3, going that way. And I went pretty quick. I don't remember what my slope is, but it should be greater than 1. It should be pretty steep. Now, if I'm going pretty quick, you might think I should graph that up here. And you would be right in the fact that it is a larger number. However, you do also have to take into account direction here. Any velocities that are positive go on this part of the graph. Any velocities that are negative go on the negative part of the graph down here. So my first velocity when I was moving from 0 to 2, I was going in the positive direction. That was a positive 1. But now that I'm going fast in the negative direction, I have to say my velocity goes down here at whatever slope number that was. Let's see, I went 5 over 2 seconds, so that's 2.5 meters per second. And the actual number isn't super important right now, but you need to see that we're going to have a bigger number because I'm moving faster, but it's going to be in the negative direction, so it goes on this negative side of the graph as opposed to the positive side of the graph. Now, last thing before we are done and you get to go do your other assignment is slope for these graphs. So we said slope equals rise over run. And right now, this graph doesn't really have a slope, but some of them that we will, that we're going to get into later will have a slope. So I'm going to erase this and draw a different graph for a different scenario that does have an actual slope. So say we have this graph. Let's talk about what this graph means. If we've got velocity and time, at time equals 0, we're starting at 0 velocity, which is rest. So we're just chilling there. But as time progresses, our velocity goes up, meaning we're getting faster and faster, and we're moving in the positive direction. We're speeding up in the positive direction. Now, if we were to find the slope of this line, we're going to find something pretty interesting. We're going to use the same method as before. We're going to do rise over run. So if I wanted to find the slope between 2 points on this line, I do rise, how much it goes up, over run, how much it goes over. Now, if you look at just the part going up, just the rise, the thing that's changing is the velocity. So your rise is delta V, change in velocity. And your run is changing time, delta T. And we're going to see later that slope equaling delta V over delta T is the equation for acceleration. So for a velocity time graph, the slope is going to be equal to acceleration. We'll get into that way later. Today we're really focusing on position time graphs, but there will be a little bit of velocity time in there as well. All right, if you've got a question, please let me know as soon as possible. You can just email in and we'll get it figured out. For now, just go do your other assignment in Google Classroom, and I'll catch you later.